Hello, everybody. This is Team 19026. We are the Automated iButton Placement Device Group, sponsored by Roche Tissue Diagnostics. This is our Virtual Design Day video.
Our team includes Jacob Sindorf, DME, Alexander Lee, ME, Merrick Perez, ECE, Cecile Flores, ECE, Jorge Gracia, SIE, and Zhejiang, ME.
This is our Design Day poster. In the following slides, we will address in detail each section that is listed. The results and how it works are seen through the system demonstration, while the content of the other sections are clearly described in the slides to come.
Roche Tissue Diagnostics, RTD, is located in Oro Valley, Arizona. They are an innovator of tissue-based diagnostic solutions for patients worldwide, where their products assist in the diagnosis and treatment of cancer and infectious diseases. iButtons are an RFID chip enclosed in steel casing used for product identification. They're actually stuck to sticky pads, which is a circular pad with adhesive glue on both sides used to stick iButtons to corresponding boxes. The current process is done manually and consumes about 4,000 labor hours a year, as you can tell right here in this video. This requires about 2 full-time employees that, due to privacy concerns, RTD cannot disclose burden rate. And we seek to significantly save RTD labor costs by automating the iButton placement process with machinery.
Our approach to the problem starts with the left diagram, which shows models and analysis we run. That includes correct FeederBowl volume, motor stepper size and torque, correct suction force, and system power analysis, or how much each electrical component requires via volts, amps, and watts. We also had an error-rated SolidWorks model and based initial designs on similar automated processes already used in the RTD facility. To guide our approach, we follow system requirements given to us by our sponsor. The table shows the system requirements. However, due to time constraint, we shall not read the entire figure in detail. Some key features are the following: ECR for sound over 60 dB FeederBowl, which was solved by implementing a soundproofing cover, ECR on system accuracy solved with sensors, and ECR on size solved by changing the overall design and allowing for a 3x3 by 4 inches. The following slide have demonstrations that help take the next steps towards addressing the DVDs, as well as some of the passes as seen in the matrix.
The system follows the numbering and labeling as seen in the system architecture and the system block diagram. Those include 5 sub-assemblies that are the user interface, the pick and place or iButton placement, the iButton FeederBowl, the sticky pad feeder and clear cover removal, and the Reroll. This document shows the specific part numbers per sub-assembly, which include the part ordering number for all non-custom parts, our personal numbers, and the screws and the screw numbers. This is the top-level drawing of the automated iButton placement device. It shows a 4-foot by 6-foot table to hold the device and a smaller custom table to hold the FeederBowl. The clear acrylic is a safety feature to prevent anyone from touching moving parts and to keep foreign objects out. The gray cover is the soundproof cover that we added as an ECR and lowers the FeederBowl sound. This drawing shows the system without covers and tables for clarity. The subsystems including the GUI, pick and place, FeederBowl, sticky pad feeder and clear cover removal, and the Reroll, which will be explained in detail individually in the following slides. Some engineering features are that the whole system uses the same ball bearings, the same sized axles, the same 20/20 adjustable frame, the same 4 varying length M3 screws, and the sticky pad feeder, Reroll, and free roller use some of the same parts. As seen in this system assembly, it shows how the subsystems are spaced and how the hardware works when put together. This specific view shows the sticky pad lined up in the placement position. iButtons are picked up from the rail using suction in the pick and place and placed on a sticky pad with a rotating servo motor, then stepped using servo motor specifically from the Reroll to line up the next sticky pad. These sensors seen here help accurately correct the system. Now for the specific description of subsystems, starting with the GUI.
Seen here is the full electrical setup for the system. First is the vibrating FeederBowl, which will be represented by a light in the next slide. Then is a distance sensor, which is located on the iButton bus. The 2 stepper motors are for the clear cover removal and the re-rolling assembly. Lastly, the diaphragm pump and servo motor, which are for picking up and moving iButtons on the pick and place. The GUI has multiple buttons, such as the test components button as shown, which individually controls each component, and the other is the start systems button. The only component unable to be tested using the GUI is the distance sensor, which requires the serial monitor and will be explained in the operations manual. All electrical components, albeit the FeederBowl, are easily obtained online, making them easy to replace and use. Here's me starting the machine using the GUI by clicking the Start System, as can be seen by the light or the feeder bowl being lit up as there's nothing in front of the sensor, and the pump is turned on and will stay on until the machine is stopped. This is me sticking an iButton to the front of the pump and then unplugging it to show that it is capable of picking up and dropping an iButton. When my hand, or in the case of the real system, an iButton rests in front of the sensor, the feeder bowl or light is seen here turns off and the motors begin to work. The servo moves from one position to another. This shows that the pick and place, which will be shown in more detail later, can go from the feeder bowl rail, grab an iButton, and then place it on the sticky pad. The servos then move a certain distance at the same time. This represents the clear cover rolling up and the re-roll pulling the tape a specific distance so that the next sticky pad is in line to have an iButton placed on it. When my hand or an iButton is moved, the feeder bowl turns on again and the motors stop until a new iButton signifies that the feeder bowl rail is full and ready for an iButton placement.
So for the pick and place, this diagram shows the pick and place in a drawing. As mentioned, the servo allows it to move from 2 points while keeping the suction cup perpendicular to the ground. This allows for accurate placement every time, as it always moves between the same 2 padded positions. In this video now, we will see the pick and place in motion. Over here you can see the iButtons, and over here is the rail from the feeder bowl. And that is how the pick and place moves between 2 spots, and how it places the iButtons onto the sticky pad. So for the feeder bowl, we actually were able to implement the stack check as well as modify the bowl to receive the iButtons. So you can see here we're loading the iButtons into the feeder bowl. The iButtons are going up the rails, and this is the stack check that's doing its work. So you can see that the ones that are double stacked get pushed off back to the bottom of the bowl and make their way up again. So for the mechanical orientation check, we weren't able to get it on the bowl itself because of certain constraints now. But we were able to get the piece that we can attach on later to make sure that the larger side is on the bottom and the smaller side is on the top. And you can see from the video it works.
This is the sticky pad feeder, clear cover removal, and reroll with the model of how the tape path would work. So it shows the sticky pad tape is moved, the clear cover is then removed, and the sticky pad plus a placed iButton is then re-rolled.
Due to COVID-19, we had a lot of issues that hindered our final deliverables. The RTD machine shop was unable to finish our SolidWorks design parts besides the pick and place, so we were unable to run a full system integration test or even assemble the full system. Communication and getting things done early are the best advice we can give to anyone doing a new senior design project. Some next steps include manufacturing the subsystems, assembling the system, testing the hardware and software integration, and fine-tuning the process.
We would like to thank our mentor, Pat Caldwell, our sponsor, Arosha, Jessica, and Gloria, and the U of A Engineering Department.